Swayam Prabha. Digital India. Educated India.
Let us start with the additional problem. Now we are going to discuss addition rule. Addition rule in the sense that suppose A is even and collect n of number of A. Suppose A1, A2 and so on, AM are a subset of A, and then n of A, n of A2, n of A3 and so on, n of AM, you have to add them so that you can get n of A will come. So, this is the addition rule. Already we discussed. Just for revisit and for solving the problem, we recollect the definition of the rule. Now, we are going to discuss one example. An engineering student undertaking a capstone project T has a choice of 4 professors A, B, C, D, who can give him a list of projects from which he can choose one. A has 5 projects, B has 7 projects, C has 6 projects, D has 2 projects. Now, since the student cannot take any other project once he has chosen a project, so the number of choice has, as per the addition rule, n of t equal to n of A plus n of B plus n of C plus n of D. We know the value of the project of A, so here is 5 and B has 7, C has 6 and D has 2, sum them, we have a 20. So, this is the meaning of addition rule applying the what engineering student taken the capstone project. Now, we have a multiplication rule same as different types of the parts, and then let it be A1, A2 and so on AM, and if you want they are functionally independent, then simply you have to multiply them. N of A equal to n of A1 into n of A2 into n of A3 and so on n of AM. Now, based on this we are going to discuss the problem. A professor assigns a capstone project T to a senior engineering students consisting of 4 parts A, B, C, D that must be done in a sequence independent of the previous ones. Part K can be done in 2 ways, part B in 3 ways, part C in 5 ways and part D in 4 ways. Since A, B, C, D are functionally independent, therefore, the project can be done in n of t equal to n of A into n of B into n of C into n of D, that is 2 into 3 into 5 into 4, which is equal to 120 ways. So, this is a way. If they are independent, then apply the multiplication rule. Now, sampling with replacement and with ordering. So, number of distinct order R tuple is n power r. Suppose they are distinct, then applying the ordered rule and then we have n power r. For example, the number of distinct order ways can draw 2 balls from an urn containing 4 balls numbered from 1 to 4 is obtained as follows. The cells corresponding to n equal to 4, the total number of balls. So, the balls corresponding r equal to 2, the number of ways 2 balls can be placed in 4 cell is simply n distinct order. Therefore, here r equal to 2 and we have a what number is n is 4 and then 4 square which is equal to 16 ways. So, these 16 order ways are shown in the following table. For example, 1 you take it corresponding 3 comma 1, 1 2 you take it 3 comma 2 will come, and then 1 3 you take it 3 3 and 1 4 you take it 3 comma 4, 2 1 you take it 4 comma 1 and 2 2 you take it 4 comma 2 and 2 3 you take it 4 comma 3 and 2 4 is 4 comma 4. So, this is a ways we can displace in terms of the table. Now, we have a combination. Number of distinct R tuples can be written as n into n minus 1 into n minus r plus 1. Therefore, NCR equal to n factorial by n minus r factorial. For example, you take a previous example and we now draw 2 balls from 4 balls without replacement and with ordering. So, the number of ways this can be done is obtained by applying NCR. So, here n equal to 4, r equal to 2, therefore, 4C2 which is equal to 4 factorial by 4 minus 2 factorial which is equal to 4 factorial by 2 factorial which is equal to what? 1 into 2 into 3 into 4 by 1 into 2. So, we get 3 into 4, therefore, what? 3 into 4 equal to 12 ways instead of 16 ways that can be obtained in the table. So, the 12 ways are shown in the table, that is the table 3 to arrange in the order first 1 comma 2, next 1 comma 3 and 1 comma 4, 2 comma 3, 2 comma 4, 3 comma 4. So, this is one way of a 6. Another 6 is 2 1, 3 1, 4 1, 3 2, 4 2, 4 3. So, reciprocate it, totally it consists of 12 ways. So, this way we can arrange the ball. So, out of 4, 2 balls are drawn in such a way that the arrangement can be done by the method of combination NCR. So, this is the inference you have to learn. Next, we have one example. In the Olympic 100 meter dash, there are 9 runners. In how many ways can the gold, silver and bronze can be given to these numbers? So, here are 9 runners or the cells N and 3 medals or the balls are R. Hence, from the previous equation 3.2.3, the number of ways that the medals can be distributed in 9C3 which is equal to 9 into 8 into 7 equal to 504 ways. So, this is the answer to the question. Next example, birthdays problem. So, we want to determine the probability that in a class size of R 2 or more birth dates match. We shall assume that the years consist of 365 days and the year birth is inconsequential. So, here 365 days in a year corresponding to n cells and the class size to R. If the class size is over 365, then 2 or more birth dates will match with the probability 1. So, that is the first statement you have to understand. Now, the number of ways the R student can be placed into 365 birthdays with the replacement is using n power R, that is 365 power R. The number of ways they can be placed without replacement 365 CR is all the birth dates are different, therefore, the probability of no 2 birth date match. Therefore, probability of no birth dates match is 365 CR divided by 365 R. So, that can be expressed in the table like this 1 2 3 1, 1 3 3 2, 1 4 3 4 and 4 2 1 4 1 and 2 3 4 2 and 2 4 4 3 that is the meaning of corresponding the table already explained, and based on this the picturization of the number of students can be written as like this. So, that is 0 to 50 students you take it, and then the corresponding the probability between 20 to 23 is 0.5073 and 23 to 30 we have 0.706. So, based on this we have to fix the probability table and we have to calculate. So, these are all the probability tables start from the age of 20 to 50, and the explanation is if P of R is a 2 or more birth dates match in the complement of the preceding equation as P of R equal to 1 minus of this no birth date, like that. Therefore, we have a graph P of R where R varies from 0 to 50, and it is tabulated from the between the 20 to 26 and 30 to 36 and 45 to 50, right. So, these are all the things to be determined corresponding to the what the graph of the probability, and note that 2 or more birthday to match. So, here the 50% chance for the 23 student and 71% chance for the 30 student and 95% chance for the 46 students can be determined. In other words, 46 students for 2 or more birthday to match with 95% probability, but to get 100% probability we need to go 366 students, because we have a 366 days corresponding to the birth date fixed. Now, let us go with another example. We continue example 3.22 with sampling 2 balls from 4 balls without replacing and without ordering. So, this means that there is no distinction between 12 and 21, 23 and 32, 34 and 43. So, thus we have the only 6 ways, and this is obtained by applying the equation 3.31. You take n equal to 4 and r equal to 2, yield what 4C2. 4C2 is nothing but 4 into 3 by 2 into 2 1, which is equal to 6, as shown in the figure of the table 1 2, 1 3, 1 4 and 2 3, 2 4, 3 4. So, this way we can do according to what the distinction between the 4 balls and out of 2 balls, and corresponding the 6 ways we can do in terms of the displaying the possibilities. Now, we have an example, call it as a Catalan numbers. The numbers, there are n objects to be placed in a computer stacks in the following way. These objects are first stored and deleted later, with the result that when all the n objects are deleted, the stack is empty. Hence, the operation store S has to precede the operation delete D, and at any point along the stack, the number of stores should always be more than or equal to the number of deletes. So, finally, the stack should begin with the store and end with the delete. So, we need to find the number C of n of operations required for n objects. So, for example, if you take n equal to 3 object, so the number of way of ordering the store and delete the operation are 2 into 3 is 6. So, the letters are triple S, triple D, and S associated with D, S associated with D, S associated with D is another ways, and another one is 2S, 2D and ST. So, last 2 only change, and ST, SS, DD, the first one change and rest of them successively coming, and then first and last same and in between change, and everything is changed, so ST, ST, SST. So, these are all the possibilities we can do for what fixing of the changes of the ordering, and let us having the operation start with S and end with D. To no point along the chain can be numbered as a D operation and exceed S operation. So, we have to show that C of n is 1 by n plus 1 into 2n factorial by n factorial into n factorial. So, the total number of 2n operation we have developed. The total number of ways that can be obtained n combination is 2n Cn. Out of this combination, there will be many realization in which the number of D's will exceed the number of S. So, we will now find the number of ways in which D's will exceed S. So, if we are at the point of n plus 1, we have the stacks of say the table 1 shows that first you start with the number 1, the stacks is 1, 2 we have a 2, if you take a 3 they are having a 5 stacks will come, if you take a 4 it becomes 14, 5 42, 6 132, 7 429. Simply apply the formula previously we described this C of n equal to 1 by n plus 1 into 2n factorial by n factorial into n factorial, apply the number n so that the answer will come in the stacks. So, similarly go for 8, 9, 10, 11 and so on 20, the corresponding stacks of the values we evaluated and we calculated, and this is the result. We can understand the meaning of the possibility of the stacks. Now, along the stacks the number of ways D will exceed S will be 2n C n plus 1 equal to 2n C n minus 1, both are what conjugate to one another. Hence, the number of stacks is 2n C n minus 2n C n minus 1 equal to 1 by n plus 1 into 2n C1 is a general format of the combination. So, this idea is called as Catalan number, the pattern 1, 2, 5, 14, 42, 132, 429, one pattern generated. This pattern is nothing but Catalan number pattern. So, somebody may ask that what is the meaning of Catalan pattern? The Catalan pattern may comes with the help of the formula of Cn equal to 1 by n plus 1 of 2n factorial by n factorial into n factorial. So, this is the ideas we can generate in terms of the probability using the combination. Now, let us go with the another example. It is an interesting equation. So, we tackle the different kind of problem. How many solutions are there to find the equation of x1 plus x2, x3, x4, x5, x6 equal to 24. See, it seems to be Ramanujan's problem, right, in the linear equation, the linear Diophantine equation, and then so it is actually infinitely many solutions, but when you restrict it to k equal to 1, 2, 3 and so on 6, and we have a lot of cases, based on the cases how many solution can be generated, that we are going to discuss in deeply in terms of the permutation and combination using the probability ideas. Now, we have a lot of assumption. We have to take xk is greater than 2 for all k, and if suppose if xk is greater than or equal to 3 for all k, therefore, we have the possibilities of totally 6 equation and start from xk equal to 3, therefore 6 into 3 equal to 18 of the required total of 24. Let us equation solving x1, x2 and so on, x6 equal to 6 is an unrestricted manner. So, here we identify the equation, that is 3.217 is this, and then when n equal to 6 corresponding to the number xk, if you take r equal to 6 corresponding to the right hand side of the equation, so that what happened, n minus 1 plus k divided by c r is equal to here 6. So, 6 plus 6 is 12, 12 minus 1 is 11, 11 c 6 and 11 c 6 and is equivalent to see 11 c r equal to n c n minus r. So, here 11 c r is equal to 11 c 11 minus r. So, r equal to here r equal to 6, therefore, 11 c 11 minus 6 equal to 11 c 5 will come. So, therefore, 11 c 6 and 11 c 5 are equal. Therefore, after simplifying the combination of 11 c 5, so we have 462 is a net value. Now, we have a lot of possibilities of x1, x2, x3, x4. Suppose x1 is greater than 2, x1 is greater than 2, x2 is greater than or equal to 1, x3 equal to 3, x4 is greater than or equal to 4, x5 is greater than 2 and x6 greater than or equal to 2, what happens? Another case. Now, using x1 is greater than or equal to 3 and x3 is greater than or equal to 4, x5 greater than or equal to 3, the number of restriction add up to 3 plus 1 plus 4 plus 4 plus 3 plus 2 equal to 17 will come. Check it out in the equation. First 3, 1, 4, 4 substitute, 3 substitute in the equation. So, 17 will come. So, this leaves totally 24 minus 17 equal to 7 unrestricted choices will come. Hence, the number of solution is n minus 1 plus number what you have taken C 7. So, here 6 minus 1 plus 7, 7, 6 minus 1 is 5, 5 plus 7 is 12, 12 C 7, 12 C 7 and 12 C 5 are equal, therefore, the value is 792. Next, if x2 is less than 5 and x3 is greater than 10, so the number of balls that can be drawn with the restriction x3 greater than or equal to 11 corresponding to n equal to 6 or equal to 24 minus 11 equal to 13, and then we have 6 minus 1 plus 13C 13 is 18C 13 which is equal to 18C 5 which is equal to 8568. So, the number of draws that violate the additional restriction x2 is less than 5 is obtained by first finding the number of draws with additional restriction x2 greater than or equal to 6. Therefore, the number of ways corresponding to n equal to 6 and r equal to 24 minus 11 minus 6 is 7 is given by 6 minus 1 plus 7C 7 equal to 12C 7 which is equal to 12C 5 which is equal to 792. Based on these ideas, and we have a restriction of x3 is greater than or equal to 11 and x2 is greater than or equal to 6. Therefore, we have to subtract them from the previous value 8568 to 792, we have 7776 ways generated. Now, we have an example. Here is an interesting example to illustrate the versatility of the formula in the equation 3.27. 4 dice each with only 4 faces marked 1, 2, 3, 4 are tossed. We have to calculate the number of ways in which the tosses will result in exactly 1 number, 2 numbers and 3 numbers and 4 numbers. Showing on the faces of the dice without regard to order and replacement, the total number of ways is tabulated. So, the interesting one is 4 faces marked 1, 2, 3, 4. Now, let us start. Suppose all the faces are 1, 1, 1, right? All the faces are 2, 2, all the faces 3, 3, all 4, 4. Therefore, 4 single digits will come. Now, the other possibilities of first 3, 1 and second one is 2 and first 2, 1, second 2 is 2, 2, first one is 1, rest of them is 2, 2 and first all these are 3 and 3 and first 2, 1, 3, 3. So, this is the possibilities of other. Similarly, go to the phase 2, 2, 2, 2, 3 and 2, 2, 3, 3 and 2, 3, 3, 3 and 2, 2, 4 and 2, 2, 4, 4. So, because the 4 dice each with only 4 faces marked 1, 2, 3, 4 and the tosses will result exactly 1 number, 2 number, 3 numbers, 4 numbers. For that purpose, the method is like this, and other possibilities is 3, 3, 4 and 2, 2, 4 and 1, 3, 4, 4 and 3, 3 and 1. Next one is 3 4s and 1, 2 4s 2 1 and 1 4 and 3 1 and 4442. So, now you calculate totally 4 plus 4 plus 4 plus this totally 18 will come, because one more extra term is associated with 11332244. Therefore, we have 16 plus 2 is 18. So, 18 double digits will come. So, based on that we have other triple digits are 1123, 1134, 1142, and based on 2234, 2241 and 2213, and here 3341 and 3312, 3324, and here 4412, 4423, 4431. So, here how much that is 3 into 4, 12, right, 12 triple digits will come, and all are different is 1, 2, 3, 4, therefore, 1 quadruple digit. So, quadruple means 4 different digits. So, it is these are all the possibilities of the phases when we tossed the coin. So, the result is exactly 1, 2, 3 and 4, and these phases with related to dice regarding the replacement of the numbers, and this can be tabulated like this. Now, we can see the table that there are 4 single digits, 18 double digit, 12 triple digit, 1 quadruple digit, totaling 35 arrangements. Without regarding to the order and the with the replacement, the problem can be stated as follows. 4 dice each with 4 faces are tossed without regard to order and with replacement, and find the number of ways in which number 1 this can be achieved with n equal to 4 and r equal to 4 in the equation. So, the number of ways is 4 minus 1 plus 4 C4 equal to 7 C4. 7 C4 is nothing but 7 C4 minus 7 minus 4 is 7 C3, which is equal to 35. So, which is agrees with the total number of in the table. Now, we have exactly one digit is present with n equal to 4 and r equal to 1. Therefore, the number of ways is n is 4 minus 1 plus r is 1, C1 equal to 4 C1, 4 C1 is 4. So, which agrees with the table. And third possibility is exactly 2 digits are present. So, the number of 2 digit can be drawn from 4 digit is 4 C2. The number of ways any particular 2 digits, for example 1, 2 you take will occupy 4 digit number is the restricted case in the example, with both 1 and 2 occupying 2 slots, and the rest of the 2 remaining unrestricted with n equal to 2 and r equal to 4 minus 2 equal to 2. Therefore, the number of ways for this particular sequence is 1, 2 is 2 minus 1 plus 2 C2 equal to 3 C2 equal to 3. Therefore, the total number using all the combination is 4 C2 into 3 C2, which is equal to 6 into 3 equal to 18 ways. So, this agrees with the table with exactly 3 digits are present. So, the number of ways 3 digit can be drawn from 4 digit is 4 C3 equal to 4 ways. The number of ways 3 digit can be arranged from 4 slots such that all the 3 digits are present is again given by the restriction formula 3 minus 1 plus of 4 minus 3 C2 is 3 C1 equal to 3. Hence, the total number of ways is 4 C3 into 3 C1 equal to 12. So, exactly 4 digits are present. So, the number of 4 digit will present is obtained, the argument item is given by 4 C4 into 4 minus 1 plus 4 plus 4 C0 equal to 1. So, this is the things we can calculate with the help of the combination of the digit 1, 2, 3, 4. Now, making use of the generalization of these ideas, use the example 3.36 can be generalized to the tossing of n-sided dice. Imagine it. So, n can be any number, you can take it. So, total number of sample points without regard to order and with replacement is n minus 1 plus ncn equal to 2ncn. So, out of this, the number of ways exactly odd digit will occur can be derived as follows. So, the number of way of odd digit can be chosen, n is NCR. If any particular sequence of odd digit has to fill n slots, then the number of ways this can be done is obtained by r equal to n minus r. So, this yield r minus 1 plus n minus r c n minus r equal to n minus 1 c n minus r. So, this is the generalization of the digits. Now, we have a picture, we have a n-sided die thrown n times and taken into account of the numbers 0 to 8. Suppose you start with 0, right. The k number of digits represent column wise and row wise n side die thrown n times. For example, 1 1 we have 1 will come, 1 and 2 is 2, like that 1 and 8 is 8, and if 0 is associated with 1 is 0, whereas 1 to 1 is 1 only, 2 to 1 no possibilities, 3 to 1 no possibilities, 4 to 1 no possibilities, 5 to 1 0, 6 to 1 0, 7 to 1 0, 8 to 1 0. Now, we have the possibilities of the first column is 1 and go ahead with the second column, and 0 2 is 0 only, 1 2 is 2 times, therefore 2 will come, 1 to 3 is 3 times, 1 to 4 is 4 times, 1 to 5 is 5 times, 1 to 6 is 6 times, 1 to 7 is 7 times, 1 to 8 is 8 times. Now, we have a corresponding value, and 2 to 2 is only 1, 2 to 3 is 6 times, right, 3C2 will come, 2 to 4 is 2 to 4, 2 to 4 is 18, we saw that. Similarly, proceeding in this way 40, 75, 126 and 196 will come. So, this is the technique you have to use, and you see the main diagonal start from the 1 to 1 is 1 only will come, and then the first column except 1 everything is 0, and below the diagonal all the values become 0, because the number corresponding 3 to 2 compare with 3 and 2, 2 is lesser than 3, therefore 0. So, up to 7 the value becomes 0, because 8 and 7, whereas 8C8 is 1 will come. So, this way we can calculate the n-sided die thrown n times corresponding to number of digits we can calculate. So, this table can easily understand the k number digits to n-sided die thrown in n times. So, this is the sequence of NCR sequence are functionally independent. The number of ways capital N NCR is as follows. Capital N of NCR is NCR equal to n minus 1 C n minus R. So, the equation 3.10 is n of n comma r tabulated n equal to 1 to 8, where r equal to 1 to 8 in the figure. So, in addition we have the following interesting identity. Combining equation 3.38 and 3.39, we have 2n minus 1 C n equal to summation r equal to 0 to n NCR into n minus 1 C n minus r. So, this equation can also expressed by substituting m equal to n minus 1, r equal to n and k equal to r in the Vandermonde identity. So, this identity using, so that n plus m C r equal to summation k equal to 0 to R NCK into MC R minus K equal to n plus n minus 1 Cn, which is equal to summation k equal to 0 to n NCK into n minus 1 C n minus K. So, this is the picture representation with van der Monde identity. Now, we have a Bernoulli trial. Already we discussed, based on that we have to discuss some example. So, tossing an unfair coin 4 times constitute 4 Bernoulli trials with heads S and tails F. Therefore, P of S equal to P and P of F equal to 1 minus P. Therefore, the sample space S is a Cartesian product of ordered 4 tuples. The cardinality is represent 2 power R here, 2 power 4 is equal to 16 points. So, this is the meaning of Bernoulli trials of tossing 4 coins at a time. Suppose tossing a die 5 times can be considered Bernoulli trials. So, we define the probability of success is 1 by 6, not getting an IS as a failure. Therefore, 1 minus 1 by 6 is 5 by 6. So, the resulting sampling S is the Cartesian product. Therefore, it should be the ordered in quintuples. So, the number of points equaling the cardinality is 2 per 5 equal to 32. Now, we have a problem. A single die is thrown. The probability of getting an ace is P equal to 1 by 6. And the probability of not getting the ace is 1 minus 1 by 6 is 5 by 6. So, the experiment is Bernoulli distributed. Now, we have a problem. A fair die is rolled 10 times and we will calculate the probability that an ace comes up exactly 4 times. So, here P equal to what? The die is rolled. Die is rolled is one face get it 1 by 6 and not getting the face is 1 minus 1 by 6 is 5 by 6. Therefore, P and Q we can write directly, and if we have a die with 10 times rolled, therefore, n equal to 10. So, obviously, it is a Bernoulli trial and exactly 4 times ace is comes, therefore, k equal to 4. Then we have a rule to obtain 6 aces in 10 trials, then formula is n factorial by n is 10 by what 4 that is totally 6 phases, therefore 6 factorial, and here k is equal to 4, therefore k factorial is 4 factorial into p power 4 into q power n minus 4 is 6, therefore 1 by 6 whole power 4 and 5 by 6 whole power 6. We have what the value of after simplifications 0.05427 will come. Next, the probability that at most 4 aces show up. So, the probability 1 above we wanted exactly 4 aces coming up. Now, we are looking into probability of 4 or fewer aces showing up. Therefore, the probability is obtained as follows. So, probability of number of aces less than or equal to 4 is summation k equal to 0 to 4 10 factorial by k factorial into 10 minus k factorial into 1 by 6 whole power k into 5 by 6 whole power 10 minus k. So, the value is 0.98454. Next, the probability that the number of aces showing between 2 and 6 inclusive. Between 2 and 6 means probability of 2 less than or equal to x less than or equal to 6. And the notation for binomial Bernoulli trial is B of k 10 comma 1 by 6. Here n equal to 10, chances is 1 by 6 and k is based on the between 2 and 6. So, this indicates the summation, the formula P is less than or equal to number of A's less than or equal to 6. So, generally the formula is denoted K starts from 2 to 6 because lower limit 2, upper limit 6, therefore 2 to 6, and then here n equal to 10, therefore 10 factorial by k, that is you have to choose the between them, therefore k factorial into 10 minus k factorial. In one phase is 1 by 6 and not getting the phase is 1 minus 1 by 6 is 5 by 6 and maximum is k, therefore k substitute then 10 minus k. So, if you start k equal to 2, k equal to 2 substitute here and k equal to 3, 4, 5, 6 and so on substitute it, sum them, then the result is 0.22451. So, the graph of probability mass function can be generated shown in the following figure. Also cumulative distribution function also shown in the following figure, and you see that this is the stage between 0 to some point, and corresponding what expression in the probability is 0.15, in between that 0.1 to 0.2, and then this value is between 0.8 to 0.1 point something, similarly 1 point something to 2 point something, and go ahead, finally it reaches the probability 10 and maximum level of what 0.3 or something like this, that is they generated with the values of 0.2245651, and substitute all the value corresponding graph we can demonstrate it, and we have to combine together of 0 to 1, 1 to 2, 2 to 3 and so on up to 6, so that the cumulative probability of k is less than or equal to 10. We have a success in the 10 trials. So, this way we can demonstrate the graph in terms of the probability distribution in the Bernoulli trial, and based on this we can easily predict in the interval from 0 to 10 and corresponding 0 to 0.4 the solution to the problem. Now, we have another example. Two experiments are performed. In the first experiment 6 Faradays are tossed and the person wins if she gets 1 or more aces. In the second experiment 12 dice are tossed and the person wins if she gets 2 or more aces. So, we want to find in which experiment the probability of winning is higher. So, we calculated with the help of the Bernoulli trial and choosing the k, n and p, and n, p is 1 by 6 and corresponding calculate, n is a number of trials you have to do that, and k you have to choose either 0 or 1 or 2 and so on 10, and simply substitute in the Bernoulli trial, and once you have to do manipulate and computationally do that, and more or less they are equivalent to one another. This is the experiment of the probability of winning is higher and calculated. So, the probability of getting 1 or more aces out of 6 tosses is same as complement of the probability of getting no aces in 6 throws. So, this is obtained in the equation n equal to 6 and p equal to 1 by 6, q equal to 5 by 6. Therefore, 1 minus probability of no aces in 6 throws is equal to 1 minus 6 E naught into 1 by 6 whole power 0 into 5 by 6 whole power 6 equal to 0.6651. So, the probability of getting 2 or more aces is 12 throws is same as the complement of the sum of the probability of getting no aces, and 1 ace in 12 throws with n equal to 12. We have 1 minus p of no aces in 12 throws minus p of 1 ace in 12 throws. So, the probability is 1 minus of 12 C naught into 1 by 6 0 5 by 6 whole power 12 minus 1 minus of 12 C1 1 by 6 whole power 1 5 by 6 11, and simplify 12 C naught is 1, 1 by 6 whole power 0 is 1, 5 by 6 whole power 12 is 0.1122. Similarly, 12 C1 is 12 into 1 by 6 into 5 by 6 whole power 11, and substitute simplify, you have 0.6186 will come. Hence, the probability of getting one or more aces in 6 throws is better than the getting 2 or more aces in 12 throws.